Today, we're going to review some solubility terms and look at some notes regarding that and take a look at solubility curves. I told some of you yesterday that normally we would do a lab with this and we would build our own solubility curve. But that's kind of hard right now because we're not at school. So I'm going to show you the notes, and I've also posted them to the assignment. The notes I'm going to show you, and then you're going to do the questions that accompany a solubility graph that's posted with this assignment. So let me share or present these while I'm talking. And hopefully this will be a good as well for some of the terms that we've already discussed back at the beginning of this chapter. So just to review, what is solubility? If something is soluble, it means it's dissolving in something else. So we use our term solute, and that's the substance that gets dissolved, and it gets dissolved into the solvent. And we kind of express it as a rate. Now, we did not discuss this a whole lot, but as far as a rate, now I want to show you that when you do these solubility graphs, you're not going to use molality. It's a difference. So there's kind of a standard way to compare all solutes with their solubility in water. And what scientists do is they take a look at how well substances dissolve. So in this case, 36 grams of sodium chloride per 100 grams of water. And then at 20 degrees. And 20 degrees is just kind of the acceptable room temperature in degrees Celsius, as opposed to, close to, 68 or 70 degrees Fahrenheit. Okay. Now, what are some things that will affect solubility? Temperature. Now let's review. Temperature is one of the major factors. And if you think about solid solutes, such as table salt or potassium chloride or magnesium chloride, those are solids, crystal structures, typically ionic compounds, but you can have something like table sugar, which is not ionic, that you would want to maybe dissolve in water. You make sweet tea, dissolve sugar in your tea, that kind of thing. So it's not limited to ionic compounds. Now, what happens as you increase the temperature of your solution? Well, the solubility is going to increase. If you increase the temperature of your solution, the solubility will also increase. So there's a directly proportional relationship there. As temperature increases, the solubility increases. Because what's happening is if you increase the temperature, you're going to allow for an increase of energy. That gets those particles moving faster, and they spread out more. So there's more spaces, and those molecules can get surrounded by the solvents, and more solute is going to be surrounded by more solvent. And it just allows for the solubility to increase or perform better. Okay, that's for solids, but for gases, it's the opposite. For gas solutes, like carbon dioxide into water, for example, to make your soda or sparkling water, as temperature increases, the solubility decreases. That's why you don't want to drink a hot soda. Or if you leave a soda on the table and you walk away, you forget about it, and you come back and it tastes that idea of a flat soda, that's because, kind of for the same reason, those particles move faster and faster, including those gaseous particles, and they start popping out of your solution and just head up into the air around you. So that carbon dioxide starts moving faster and faster and faster and bebops on out of there into the air. And so then you have a flat soda and extra carbon dioxide molecules running around in your house, okay? So more kinetic energy, particles move faster, spread out more, and it floats away from the solution. All right, so that's dealing with temperature. The warmer the temperature, the greater the solubility for solids. The warmer the temperature, the lower the solubility for gases. All right, now, what about pressure? Pressure is not as great of a factor as temperature. But we can read this a little bit here, but you're not, I mean, in everyday life, you don't see that much of a change in pressure in your everyday life. Now, if you're going to a laboratory or you wanted to dissolve more carbon dioxide into a soda, then yeah, you could change the conditions a little bit. But if an increase in environmental pressure occurs, that's going to cause the particles of a gas to become more soluble. All right. So if you are a soda bottling company, you want a low temperature and a high pressure to get as much CO2 as you need into your liquids. If you decrease that pressure, the gas is going to be less soluble, which is also why some of the cans are slightly pressurized before you open them. All right. Now moving on a little bit to these, to review these. Saturated, that means the solution has all it can hold. Unsaturated means it could hold more. And supersaturated is by some way you've managed to get that solution to temporarily hold more solute than it should. All right, now, we just went through these. Maximum saturated, it's got all it can, maximum number. So a saturated solution cannot dissolve any more. There's no more space for it to fit. Okay. Now these particles down here are actually collecting because they can't dissolve anymore because the solution's full. Okay. Now an unsaturated solution means you can hold more, so there's no collection on the bottom. So here's saturated, just perfect. There's no collection on the bottom. Here's unsaturated, has room for more. Now, a supersaturated solution contains more solute than what would normally be the case, the normal saturation point. So remember, go back to the idea of what happens if you heat a solution that has a solid particles dissolved in it. If you heat it, that solubility goes up. So that is how you would have to make a supersaturated solution with a solid solute. Heating a solution, here you go, heating a solution will cause particles to spread out, allowing more solute to fit into spaces between solvent particles. The extra heat creates kind of like an artificial scenario in which more solute can dissolve. When the solution cools, the solutes will crystallize and fall out of solution. So this is one way you make, I don't know if you guys know what rock candy is or not, but it used to be one of my favorite little treats. And that's how you make rock candy. You get a supersaturated sugar solution, you let it cool, and those crystals of sugar come out and they stick to that string or that stick into that yummy sugary goodness, crystals all built up and down. Okay, now here is a simple solubility graph. There's just one thing on here, and that's the solubility curve for potassium nitrate. So here is this curve, and you'll see that we've got degrees Celsius on our x-axis and solubility on our y-axis, and it's grams of solute per 100 grams of water. So we're assuming there's 100 grams of water dissolved, and how much solute can be dissolved in those 100 grams of water. All right, anything on this line, the green line here, represents a saturated solution. Any circumstances down here, whether it's mass or mass and temperature area, that would allow you to fall in this to the right of that green line means it's unsaturated. Anything over here that's dissolved would be a saturated to supersaturated solution. So here we go. Let's look at this. Which term describes a solution containing 30 grams of potassium nitrate dissolved at 40 degrees Celsius? So here's what I'm going to do. I'm going to go to 40 degrees Celsius, and then I'm going to come up here to find 30 grams, and it's right there. So look, it's to the right of the line, or it's below the curve. So that tells me it's unsaturated. Now here is what you're going to see in your activity, a chart very similar to this, where you have multiple solutes and you're trying to see what the solubility of these solutes is in water. So they're all dissolved in water. So it's our comparison of grams of solute per 100 grams of water for all of these substances here. So here's what you should, just some things to look for. Which substances are more soluble as the temperature increases? Which are less soluble as the temperature increases? So you're looking for changes going up as the temperature and mass increases. That tells you which ones are more soluble and what happens as the temperature increases. But look, there are a few that dip down. There are some that don't, that actually the solubility doesn't increase. Now, ammonia is a gas, so that should make sense. The solubility of ammonia is going to decrease as the temperature increases, right? Now, look right here. This line right here is an exception to our solid solubility rules. This is a solid, but its solubility actually decreases. This is the exception, all right, to that rule. So let's go over a few more questions. Remember, Y is how much solute grams in 100 grams of water is dissolved, and this is our temperature in degrees Celsius. So let's look at one more question here. What mass of sodium nitrate will dissolve at 60 degrees Celsius? So I've got to be a little more observational now because I have all of these substances graphed here. But here's my curve with NaNO3. All right. So I'm going to come down here to 60 degrees. And I know what mass of sodium nitrate will dissolve at 60 degrees. So I'm going to come follow my 60-degree line all the way up here to sodium nitrate. And it's just above the 120, almost at the halfway point between 120 and 130. All right, so I'm going to say 125. That's a good estimate. All right, now here's a different way of answering or being questioned. What temperature is required to dissolve 59 grams of ammonium chloride? All right, so I find my curve. Here's ammonium chloride. This time I'm going to look at my mass. I'm going to look at the y-axis. I'm going to find 59, which is just about here. And I'm going to come across, try to match it up as much as possible. And it looks like right here is where I intersect. And if I come down, I see that it's about 70 degrees Celsius. All right. Now, here's a little bit of math for you. Not too much, just a little bit. We're almost done here, guys. Hang with me. So in this situation, it says use the graph's mass and temperature to set up a proportion to estimate the solubility of a second mass or temperature. All right, so just keep in mind, this is degrees Celsius, and this is grams per 100 grams of water. So here's the question. When making a saturated solution of potassium iodide, so let's find potassium iodide is all the way up here. Look at just that little line, all right? What mass of potassium iodide will dissolve in 150 grams of water? Now, this is for 100. We want to know what happens if I increase the volume a little bit. How much more can I dissolve? So I'm going to set up my proportion. So I'm going to say, okay, at 15 degrees, which is about halfway between 10 and 20 here, let's come on up. So if I have, for 100 grams of water, I can dissolve about 140 grams of potassium iodide. All right. So I'm going to set up my ratio. I'm going to say for every 141 grams of potassium iodide, okay, just over 140, I can dissolve in 100 grams of water. That's what my chart says right here. So if I increase that to 150 grams, there's my ratio. 141 over 100 is equal to X. How much more? Because I'm adding more volume. So I do my division, I cross multiply, and look, it goes up a little bit from 141 grams to 211.5 grams. All right. How much more solute can dissolve? All right, so this is another way we can approach this problem. So here's the question. How much more potassium chlorate can be added to a solution that contains 20 grams dissolved in 75 degrees Celsius? Okay, break this down a little bit. Where's potassium chlorate? Where's my curve? Right here. Okay. Now, what I have done so far is I've added 20 grams at 75 degrees Celsius. So let's come down here to 75 degrees and let's go up and see what our saturation point is, or what our saturation mass is. Look, right here. We should be able to dissolve, about 35 or 36 grams. Okay, maybe 34. Just eyeball it, get a very good estimate. So I only have 20 grams in there. So all I'm going to do is I'm going to say, okay, well, I could do 36. I only have 20. So I should be able to add about 16 grams. Now, if you estimated and you found this to be 34 grams and you put 14, no problem. You've justified how you got that by putting 34 instead of 36. And again, it's an estimate because it's not a extremely precise graph. I actually probably, as I look at it, I probably would say something like 33 or 34. But as long as you can show me your work and understand how you got there, you're A-okay. All right, now I'm going to stop sharing this now. And I'm going to come back full screen and just tell you that your assignment is to complete the questions that are attached to this with this assignment. The solubility curve is one document, it's a PDF file, and then you have the questions that are associated with it. And there's about 30 of them, but they all relate to that graph. Okay, so do those. Those are going to count. We're going to make that a lab, and it's going to be your first lab grade for the fourth quarter. You have Friday off. Yay, enjoy it as much as you can as you're stuck at home. And I will plan on, there will be no office hours and no new video on Friday. And we will see you back here on Monday. And I hope you guys have a great weekend and you get some rest or caught up on any work that you might be behind on. And I will talk to you on Monday. Or if you're watching this early on Thursday morning, I can talk to you during office hours on Thursday morning. Talk